Welcome. We would like to thank you for taking your time to review the results of the NEOS GeoSolutions analysis of the western portion of the Neuquén Basin in Argentina. As you can see in this slide, the analysis was done on the 5 blue concession areas that are located in the extreme western portion of the Neuquén Basin, abutting just to the west the country of Chile. The area covers approximately 18,600 square kilometers, over which we acquired gravity, magnetic, and hyperspectral data for analysis. The basin fill is shown in this schematic cross-section, with the line of section shown in the lower right-hand side of the slide. The Paleozoic basement throughout the basin is overlain by alternating sands, shales, and a few carbonates of Jurassic and Cretaceous age. One of the major takeaways from this is that the 3 major source rocks within the basin, also the focus of present-day unconventional exploration, are the lower Jurassic Los Molles, the upper Jurassic Vaca Muerta, which extends into the lower Cretaceous, and the upper and lower Agrio shales within the Cretaceous. Hyperspectral data was acquired across all 5 of the concession areas. A subset of this data is shown in the upper right-hand side of the slide, outlined in red. The middle and left-hand plates are expanded views of this outlined area, with the middle plate being the very generic geologic map and the left-hand plate being a mosaic of hyperspectral data demonstrating the immense amount of detail that's possible for surface analysis. If one outlines only a few of the outcrops from the left-hand plate and then superimposes those outlines on the geologic map shown in the right-hand plate, it is readily obvious how much additional detail was made possible by the hyperspectral data. These same data were analyzed for lithology, and 2 examples are shown in the right-hand plate, the limestone member and the sandstone member, annotated by the arrows. The hyperspectral data was used to view various properties of the outcrops. On the right-hand side, we see the Mollechinko and Agrio as they appear in the generic geologic map. The left-hand plate is the Mollechinko in extremely varying greens and blues, which upon inspection turns out to be variations within the weathering of the Mollechinko. The surrounding Agrio appears as an extremely banded formation. Upon examination, these bands are variations in the amount of sands versus shales deposited within the Agrio. Remember, the left-hand plate is a 2D view of an anticline that has been seriously eroded. Consequently, we are allowed, as the bands show, to look internal to the Agrio and define properties of deposition for that formation. In order to evaluate total organic carbon for 2 of the 3 major source rocks, the Agrio and the Vaca Muerta, a number of surface samples were taken. The surface samples were divided as to being less than or more than 1% TOC, and then the spectral thumbprint of each sample was taken. Shown in this slide are the end members for the Agrio and the Vaca Muerta that define the range of thumbprints, if you will. These thumbprints, or end members, were then used to classify the variations in total organic carbon for these 2 source rocks. This slide is one of the results of the said classification. On the right-hand side, we can see that red, yellow, and blue are high, moderate, and low TOCs. The slide itself is dominated by the outcrop of the Agrio formation, but within the oval we see an outcrop of Vaca Muerta. The reds, the yellows, and the blues, because this again is a 2D version of a eroded 3D anticline, we are seeing internal to the Vaca Muerta and internal to the Agrio. we can also assess the variations in the amount of total organic carbon material deposited within these two formations. The indirect hydrocarbon indicators of surface seeps or of micro-hydrocarbon seeps were analyzed throughout the area. The El Molar block, shown in the right-hand plate and outlined in blue, is expanded in the left-hand plate. The hyperspectral mosaic is overlain with the location and the type of indirect hydrocarbons found in this area, being altered clays in green, irons in red, and calcites in blues. After further classification, we see in this slide for El Molar block the most likely position of seeps and microseeps. In green, we see locations that have 2 of the 3 indirect hydrocarbon indicators. In yellow, we see locations that have all 3 indirect hydrocarbon locators. And in the red dots, we see the location of where the actual wavelength thumbprint of liquid hydrocarbon was found. Gravity data was acquired across the area. After processing, the complete Bouguer anomaly data is shown in this slide. It's characterized by a high-density ridge that extends from southeast to northwest. The deep blues and the greens are most likely thicker sediments, with the sediments to the west of the trough being essentially the thicker sediment Lonquepay trough, and the greens to the north, the northeast, and the east being subsets of thicker sediment formed by the various thrust faults that permeate throughout the Agreo fold and thrust belt. If one applies the appropriate filters to the Bouguer gravity, one can get a representation of the geologic features in the faulting versus depth. Such a set of views is shown in this slide. The left-hand plate shows the 25-kilometer depth view. The middle plate shows the 20-kilometer view, and the right-hand plate shows the 15-kilometer view. What we see in the left-hand plate is the annotation of the Lonquepay trough, which is the thicker sediment area to the west of the Agreo fold and thrust belt. By interpreting the maxima of these gravity, we see the major faults, one of which in the left-hand plate is indeed the western Agreo fold and thrust belt fault separator. It separates the Lonquepay trough from the fold belt itself. The middle plate shows the Agreo fold and thrust belt itself and the eastern Agreo fold and thrust belt fault. The right-hand plate shows the Cordillera lineament, which is a major lineament that extends from the northwest to the southeast throughout the region. This slide is a representation of 5 different filtered data sets from the Bouguer gravity, the interpretation of which is shown in sequence from the upper left to the lower right. What we are seeing are, in the upper left, the faults at 25 kilometers. The middle upper is about 20 kilometers in depth, and the green annotates the fault at that depth, showing additional faults beginning. The upper right plate is about 12.5 kilometers, and in the red we see additional faults. We also see fault movement of the deeper fault planes. The lower left and the lower right plates are respectively 7.5 kilometers deep and 5 kilometers deep, with a continuation of the number of faults we see initiating, the number of faults that are branching, and continued movement in existing fault planes. So if we look at the plates from the upper left to the lower right, what we see is a depth representation of the faults within the study area. In order to define areas that have very little intrusives, it is possible to take the magnetic data and filter it just like we did the gravity data in the preceding discussion. In this slide, the left-hand plate shows the magnetic RTP data having had a 30-kilometer low pass applied. This provides a signature of 6-kilometer and deeper sediments. The vertical striped areas are areas of low susceptibility, providing areas that have low opportunity for magnetic intrusion. The right-hand plate is an intermediate depth range, with the RTP data having had a 20-kilometer high pass and a 5-kilometer low pass set of filters applied, representing the response of a 1-kilometer to 4-kilometer block of data. And what we see here in the annotated hatchered areas is a lot of area that is available for exploration with low susceptibility, indicating the probability that within this 1 to 4 kilometer range there are very few intrusives in the areas annotated. Some seismic was available that was on the very eastern edge of the concession areas. Shown here are the interpreted seismic lines and 4 of the major faults that were interpreted. The dip of the plane of the fault is annotated by the direction of the arrow, and the seismic profiles that are shown gives a sense of what the thrust faults look like physically. We looked for data that would assist us in generating a 3D model. We found surface geologic information, very little well information, a few seismic lines but located well to the east of most of the areas of interest, a few published cross-sections. We had also acquired several hundred surface samples that we had sent to the University of Buenos Aires for evaluation. From these, we obtained magnetic susceptibilities and remanence values, also mineralogy and lithologic information from those same samples. The driving force of the model continued to be the gravity and magnetic data that we had acquired in the area. The left-hand plate of this slide represents the Bouguer anomaly data after application of a 60-kilometer high-pass filter, representing the gravity response of essentially surface to 15-kilometer deep sediments. The right-hand plate is the magnetic RTP after application of an 80-kilometer high-pass filter, representing the magnetic response of surface to approximately 16-kilometer deep sediment package. The lines of section created for the 3D model are shown in yellow and one in black. Section 8 will be the one that we talk about. Cross-section number 8 is shown in this slide. It's an east-west profile, west being to the left and east being to the right of this slide. The section itself is shown in the bottom half of the slide. If we start on the left side or the west side, we see we are in the Lonquepay Trough, characterized by thicker sediments, deeper basement, and a number of stocks and surface extrusives. Crossing a major bounding fault separating the Lonquepay Trough from the Agrio fold and thrust belt, we see in the remainder of this section 2 anticlines overlain by anticlines in the sediments, and a number of large major faults. In order to assess the validity of this cross-section, we must calculate the gravity and the magnetic properties of the cross-section itself. So we calculate the susceptibility and the density at each point across the section. We then compare these values with the observed susceptibilities and densities that were measured in the aircraft as it overflew this line of section. These comparisons are shown in the upper 2 overplots. The comparison of susceptibilities are shown in the uppermost overplot for the magnetic data. One can see that the observed data, shown as black dots, overlays the gray line, or the calculated susceptibilities. The error function at 7.6 is relatively low. So we see that there is a good comparison between the observed and the calculated magnetic data. The gravity data is shown in the second overplot, and again we see that the observed gravity data, or the black dots, overlay the gray line, or the densities calculated from the cross-section. Because the magnetic and the gravity overlays are very close in comparison, have very low errors, this cross-section will be considered acceptable. Such a method was applied to all 7 additional cross-sections, which were then taken together to create a 3D model. The 3D model resulted in the slide we see before us. In it, we see the base of the volcanics, we see the top and base of the Vaca Muerta, one of the primary intervals of interest, and the top of the pre-Jurassic basement. Additional models were generated that had several additional areas and zones of interest for the clients. After modeling and interpretation is complete, we subject all projects to predictive analytics. To do this, we divide our projects into 2 types. We have those projects that have very significant well control, large numbers of wells, a lot of production. From these wells, we can select what we determine to be the best producing wells and use those wells and the data around them as the training set to ask the mathematical question, where in our area of interest do we have a recurrence of this type of data sets? Because the Neuquén in our area has relatively few wells and very little well data, we have to take a more greenfield approach. Herein, we had the interpreter make all the interpretations from the data sets, review the data sets, meld the interpretations, and then determine what areas should be drilled, or where would be the best well locations. These locations were then used as the training sets to ask the mathematical question again of all of our data, where in the area of interest would we most likely be to have the types of data the interpreter is most interested in. A second analysis was made for unsupervised clustering, or geographically dividing the area into areas of like data sets. We have found that the output of such a clustering analysis can be quite definitive, as it usually determines some geologic or geophysical underpinning and many times looks quite like the interpretive supervised analysis. A third type of analysis is the common predictive attributes analysis. Here, using approximately a dozen measurements, attributes, and derivatives that are common to the best wells in shale plays, the question is asked, of the area of interest, where are we most likely to see these measurements, attributes, and derivatives in the areas that we are interested in? The results of the predictive analytics are shown in this slide. The left-hand plate is the interpreter supervised result. We see in the hot colors the pinks, the reds, the oranges, the areas most like the data sets that the interpreter wished to find. The right-hand plate is the unsupervised clustering, and we see that the blues and the greens somewhat replicate the best areas of the left-hand plate. We also see that the hot colors, the reds and the pinks, are a little like the left-hand plate blues. We also will note that the pinks and the reds are somewhat synonymous with surface volcanics or near-surface anomalies. This slide is a list of the top 10 takeaways after analyzing all of the data. Major opportunities, mineral and hydrocarbon, are found in number 1 and number 8. Major risk reduction technique by quantitative analysis is in 10. And the other 7 points are major risk reducing observations or processes. NEOS would like to thank you for taking the time to review the Phase 1 results from the NEOS Geosolutions analysis of the Western Neuquén Basin of Argentina.